Okay, you heard it yourself, recording in progress. Okay, so I would like to welcome everybody to the NAL First Thursday program. Today is, keeps dropping out, doesn't it? Okay, today is May 2nd and I'm your program committee lead. My name is Lisa Spence. I want to thank everybody who attended the spring social on Wednesday, April 17th. The food was great, the speaker was terrific, but the company was the best part of all. So if you missed it, we do plan on having another social in the upcoming months, so stay tuned. For our program today, all right, it's not going to work. Fine. Okay. Our program speaker for today is Miss Amy Ross. Amy's going to share with us a wealth of information about how spacesuits are designed and how they go from being soft goods to spacesuits. So Ms. Ross is currently the technical discipline lead for spacesuit pressure garments in the Engineering Directorate's Crew and Thermal Systems Division at JSC. Say that 10 times real fast. Prior to her current role, she served as the Exploration Extravehicular Mobility Unit, or XEMU, Pressure Garment Lead and Spacesuit Pressure Garment Technology Development Lead. That's a lot. She's done work on the Z2 prototype surface and exploration EVA suit development and testing, as well as on the Z1 prototype. Okay. Amy provided support for space shuttle suit gloves, launch and entry suit gloves, EVA tools for STS-100, and Space Launch Initiative crew escape suit. She has also had several rotational assignments. She served in the EVA office as the ISS EVA subsystem manager and also as the assistant chief engineer for the ISS program. She was also the technical assistant for the Life Support Systems branch. In addition to her regular duties, Amy has served as a human test subject for 12 different spacesuit configurations and was a suited subject for the first simulated lunar gravity run in the NBL. She's also certified to scuba in the NBL. Not everybody can say that, and I'm having trouble saying it myself. So Amy joined NASA as a full-time employee in 1996, following several years as a co-op student. She graduated from Friendswood High School, holds both a bachelor's and a master's in mechanical engineering from Purdue University. Any Boilermakers in the audience? Okay, there you go. And a master's in space studies from the University of North Dakota. She is a second generation NASA employee. And in her spare time, she enjoys reading, traveling, hiking, and backpacking. And she is active in dog agility as well as animal rescue. So at this point, I'm going to turn it over to Amy.
Yes, I'm going to shout, and if you can't hear me in that back row or next to the last row, let me know, because my voice doesn't carry very well. So I'm going to apologize to Lisa. I did not give her the most. I needed to update my bio, apparently. I am no longer the pressure garment technical discipline lead. I have now joined the Mars architecture team. So I am responsible for surface systems and trying to design a Mars mission. So that's my new position, and my experience with field testing and spacesuit work is serving me well in that. Okay, sorry for all those folks online. You didn't miss much. Early in my career, I had the extreme great benefit of serving as the Phasix glove certification lead. So Joe had developed Phasix gloves for a decade using 2 different vendors. And we got to a glove design that we thought was significantly outperforming the glove design that they were using on flights. And so we wanted to share that with the shuttle program and the crew office and see if they might be interested in getting that on board of a flight. We thought a demo flight, demo flight. We'd done that before with a glove called the Phase 5 glove, and it didn't do so well because of some tolerancing issues, but we wanted to try again with this glove. Turns out they liked it enough that they wanted to implement it into the missions, so in the program. And so I had to go through the certification process, and it taught me a lot about what advanced development gets you to and what the gap between advanced development and flight still is. And it's a fairly significant gap. So we got the gloves on flight SES 88. I was trying to shoot for all my testing to be done and certification complete so the gloves could fly. It was one of those kinds of hardware issues where we were closing paperwork when I was already at the Cape for the flight. So it was up to the last minute. I mean, I spent New Year's Eve watching spacesuit testing. That was woohoo! It's midnight, guys. Woohoo! Keep going. So it was that kind of an effort, and it was. Like I said, I learned a lot with that. I'm one of the few people left at NASA Johnson Space Center who can say that they've been in spacesuits in 16G, 13G, and 0G. There's not a lot of that kind of experience that can be gained anymore. We lost the zero gravity aircraft, reduced gravity aircraft, RGA, and it's really hard to understand what that interaction on a partial gravity surface is of a human in a suit working without that capability. So I have tried to share that with as many folks as I know. We've got a lot of videos, but it's not quite the same as flying the bird. So unfortunately, that's not around anymore, but we do have the NVL, water viscosity still a factor, but we can weigh out the suit so that it is 1/6 gravity. We also have the active gravity relief offload system, Argos, that you can basically put a person in and you're picking them up in the suit. So they're standing in their boots, but overall you're still kind of experiencing a simulated 1/6 gravity as well. So those are some of the test capabilities that we have at present. Another really fortunate piece of my career was that I got to be one of the test engineers for the Desert Rats Research and Technology Studies. It meant something, but we liked rats. So I was a desert rat for over a decade. And we went out to the field each year. We kind of put ourselves, they're big into these design analysis cycles now, DAX and strategic analysis cycles, SACs and things. But back in the day, we did that to ourselves. We imposed that on ourselves. So each year, Joe would kind of think about what do we want to accomplish? What questions are we trying to answer? And then what technologies do we think we want to include? And then we would frame up a analog field test around that. And we'd spend all year prepping for that, either developing the hardware, working on the operations, whatever we needed to do. We would make sure that we were doing that. And so that by the time we got to the field test, we'd done dry runs, we were ready, hardware was ready to go. We go out to the field for 2 weeks and test our little hearts out. And we learned a lot about what your requirements for a surface suit needed to look like, and not just the suit, but the rovers and the scientific equipment and the tools and all those things wrapped around into that kind of experience. So again, it's serving me very well in what I'm doing today. And then I was the first person to get to wear the suit in the NBL in the lunar gravity. I did not plan on that. I was actually sitting at home the day before going, oh, I'll watch Richard's run. It was during COVID. So, we had it on our Teams channel that I was going to watch. And then I got a call going, hey, Richard's not feeling so good. Could you do this tomorrow? And I'm like, yes, I can. You bet I can. I haven't exercised in a year, but that's okay. We'll do this. So that's what I did. So that's a little bit about me and where I come from. And I've been really fortunate to have the career I've gotten to have and do all the different kinds of things I've gotten to do, because it's been really neat. Oop. Okay, now I can't get back up. There he is. One thing that got to be very popular a while back was these I think employee ERGs, employee resource groups. One of them that they started was human-centric design. And everybody's getting all excited about human-centric design. And I was like, well, duh. You cannot be working on spacesuits and not know the human is the center of your design. So I was like, I don't think I need to attend those meetings, guys. I think I'm on that. But that is one of the special things about pressure garments. A lot of hardware you design and you don't actually have to think about the human as intimately. Okay, so when you're designing a pressure garment, the human is the first thing you think about. How does a human move? What does a human need? What is the human going to think? How's the human going to react? How's the human going to fit? All those things are central to how you approach designing a pressure garment. Okay. So here's some of the basic stuff that I'm going to go over. Some of you, this is going to be old hat. Some of you, hopefully, sounds at least a little familiar. And maybe some of you learn a thing or two, so that would be good. But we're going to talk about what a spacesuit is. And I'm going to talk specifically about planetary walking suits. And again, at Johnson Space Center, as long as we've been doing this, so it seems old hat to us, because Joe's been doing it since Apollo. I've been doing it since 1990. And it's amazing how many people on site still don't realize a spacesuit can walk. Okay, and can walk better than they did in Apollo. And I have a video I can show folks afterwards. It won't work on the PDF that I had to send on the email, but you know, it looks like people walking. It does not look weird. It looks like you're walking in a spacesuit. So it happens. It's real. It does. We've been doing it for years and years. It's not something that's scary. Here's another story about that. We spent 45 minutes at least in a meeting at the NBL because we wanted to walk from our donning stand to the pad that takes you to, what do they call that thing that drops you into the water, the NBL, right? So they call it the donning stand, but it's not our donning stand. So, you know, it was like, I don't know, 15 feet, wasn't that far. 45 minutes going back and forth, because they think EMU trying to walk. That would be stupid in an EMU, okay? No, that's not something you want to be doing. That's not something you plan to do. You try to do it a different way, safer than that. You can do it, but it's not the best plan. But our suits, we walk all over the place. It doesn't even bother us to think about walking in a spacesuit. So the fact that we were having this conversation made us very frustrated, but they didn't understand until we showed them what our suit could do. And they're like, oh, again, if you just aren't aware, you just aren't aware. So, and we'll talk about a lot of testing. There's a lot of testing involved because, as we'll talk about, you can do objective quantitative measures of the spacesuit performance, but that's not what actually says check, we're ready to go, right? What says check, we're ready to go is that your customer is ready and willing to use your suit. Okay. So we'll talk about objective and subjective data, and it's part of that as well. And then I'll talk a little bit about my experience from being a test director as well as a test subject, which in my opinion, you can't be a good suit engineer. And when I say suit, I mean pressure garment engineer. There's the PLIS, the portable life support system, and the pressure garment, right? The box people, the big, heavy, gigantic, nasty backpack, they're a different kind of breed, right? And we can talk about that. But pressure garment people, suit people, you can't be a good suit engineer without actually getting into a spacesuit. Okay, in my opinion, it's a totally unrelatable experience until you've done it. Okay, so here's that basic slide that says, hey, a pressure garment is a life support system. In fact, we like to say that a spacesuit, and I am including the PLIS there, is a spacecraft, right? The suit does the things that a vehicle does. We do life support systems. We do power. We do thermal management. We do mobility. We do, we provide the ability to get work done in space, right? All these different things that a space vehicle provides, other than launching and landing from the Earth back to it. We do those things. So basic life support, keeping your physiology happy and intact. We do that. So again, we do it by being a pressurized balloon, human-shaped pressurized balloon. Okay. And that's thing one. And we have 100% oxygen concentration to allow that at the pressures we like to operate our suits at. The EMU operates at 4.3 psi. That is higher than the Apollo suit operated at, which is 3.75 psi. And we're talking about operating suits at about 8 psi today. And Joe built what was called the zero pre-brief suit back at the end of the Apollo program in the 60s that did that very thing for various reasons, and we can talk more about that. But so oxygen, pressure, check, and number one. Other things want to kill you in space. We all know that. So the thermal extremes, micrometeoroids and orbital debris, sharp things on the space station, for example, handrails and that kind of thing, dust, rocks, all kinds of things are happy to end your day rapidly if you don't protect yourself against them. So that protection from the environmental extremes that you're experiencing when you go into space. And then the last one, which is our customer's primary one, is go do work. Okay, so providing that mobility that allows a human to go interact with their surface and their tools and produce the work that is being asked of them. Okay. Now, if you haven't seen it before, this is what a planetary walking suit looks like. We don't tend to take pictures of our suits naked. Okay, it's just not nice. So it shows more than we care to show. Like most of us, we don't want to be naked in public, but that's where you miss a lot of the good stuff. Okay, so it's hard to see the really good stuff when a suit has its clothes on, like the suit mostly does. But some of the things that you can see, and I don't think I have a pointer. I'm gonna probably come over here and just point. So sorry for the folks on the computer. I'll start over here for a minute. Mobility. When you are in a pressure garment, think scuba tank. I mean, honestly, think scuba tank. Can you make that tank rotate the bottom to the top relative to each other by just turning it? Yeah, no, not happening. Okay, so although it is a soft goods, like your arms and your legs are soft goods, they're fabric. What the cover layer tends to hide is the rigidness of that. The cover layer is always blousier than the actual structure of the pressure garment. The reason for that is to allow the insulation to do its job properly. You have to keep the gaps between the layers of multi-layer insulation to allow the vacuum to do the job of keeping the convection out, from occurring, right? And also conduction. But that makes the outside of the suit look puffy and soft. Okay, that's not how the suit is. So it's like a scuba tank to get back there. So if you want to make the two pieces of a scuba tank move relative to each other, you need to add something to it. And that something to it is a bearing. Okay, so we have bearings everywhere you need to rotate any part of a suit relative to another part. So shoulder bearing, or we call it side bearing, it's a tailoring term for the shoulder opening of a garment. Waist bearing. This is a 3 hip bearing suit. And then there's an ankle bearing, as well as the upper arm bearing and the wrist bearing. So there are bearings anywhere you want to rotate. Well, we actually don't have it at the head. You can. But there's bearings here, bearings at the ankle. If you're walking on a rocky surface, that's a good thing to do, so you can walk over rough ground carefully. There's a big debate between soft versus hard components of the suit. We did a big test that my dad was a participant in, called the swim off, back at the beginning of the station program, trying to pick which suit that we wanted to use in the station program. It was the EMU, the Ames suit called the AX5. They had an all hard suit. Even the gloves were hard components. And then we had the Mark III, which was hard upper torso, hard brief hip elements. And then you can see here, this is the Mark III, the soft arms and legs. Crew comments out of that testing was that soft goods, even though it's a stiff soft good, it's still more friendly to your joints, like your elbows and your knees, than the hard components of the AX5, for example. And Dad'll correct me if I say something out of turn, but that was what I read out of that report. And so we've been using that in arms and legs. And the reason soft goods are good there is because it's a hinge joint, right? All I can do is this. This is all I can do. It's not rotating. It's not doing anything but this hinge activity. And so in that hinge activity, you can give a nice range of motion, reasonably low torque. It's a lightweight joint. It's fairly simple to build. So it's a nice design for that joint. Okay. Another feature of the soft goods there is that if you have something you need to do, like when I'm in the EMU, I have to work really hard to get some of the switches up here on the DCM, okay, this display control module. And I can actually squish that arm joint harder and go past the standard range of motion to get that switch, okay? If you're in a suit like the X5, an all hard suit, that range of motion that's designed into that hard good suit is all you got, right? It's a hard stop here and a hard stop here, and there's nothing you're doing about it to get any further or any more range of motion. Okay. When you walk, this is something that you need to, if you don't think so, put your hand on your belt buckle and walk. And your waist, because you are offsetting your arms and your legs as you go, they will actually, your waist wiggles, okay? A little bit. If you don't wiggle your waist, this is how you walk, right? Frankenstein, okay? So if you want a natural walking motion, you want to have that waist bearing, okay? Rear entry, let's talk about that for a minute. I missed that up top. Does anybody know about the suit port idea? Okay. A lot of people think that we design rear entry suits because of suit port. No. Disabuse yourself of that myth now, okay? That is not why we design rear entry suits. What we're trying to do with a rear entry suit, first and foremost, is to provide better range of motion at the shoulder. The current suit, especially me in an EMU, the shoulder bearings are out here, okay? In fact, so your shoulder mobility kind of is here if you're just trying to, do this kind of thing. The reason for that, and you all know this, I know you do, is if you try to put on a button-up shirt without unbuttoning it, what happens? You get stuck, right? You get stuck and then you get all extra sweaty trying to get out of it, and you usually rip the thing at some point, and it's difficult. That's because your shoulders are really wide. And so if your shirt fits you like it should, when you try to get into that shirt, there's not enough breadth here to get your shoulders through. Okay, so if you want to get full range of motion in your shoulders, you need to move those bearings inboard, in toward your neck. Okay, because your shoulder mobility, if you feel your clavicle and your collarbone, all this stuff moving around, it happens from the neck. Okay, so if you want all the shoulder mobility, you need to have your bearings in at the neck, which means you can no longer don from the waist because you can't get through there if you're trying to go up from the bottom. So rear entry, you have a door in the back, you slide down in, and you get in and they close the door behind you. Okay, so that's why we have a rear entry suit, for optimal shoulder mobility. Okay, increased shoulder mobility. Okay, in the hip, again, for natural walking, you need at least 2 bearings. I like 3, but that's my opinion. Because when you have 2 bearings, when you try to lift your knee up, pretty soon you're on this upper bearing and your knee starts to go outward. So if you're trying to step up onto something, you can't just step in front of you. You have to step out to the side. So you kind of have to stand off to the side of something and then step over to it, right? It's weird. And so it takes a little more mental energy, right? And we like to design suits to use minimal mental and physical energy to move. So the more natural you can make it, the less mental energy you're using and physical energy. If you have a 3-bearing hip, you can get your knee a little bit higher before it starts to go out, because it will go out too. Okay. Step heights for rovers that are comfortable in a suit. 1G, similar to like 1/3 G, is probably about 7 to 9 inches depending on the human. You can get into a 16G rover that's stepping out of like 12, 13 inches, just because you're not stepping, you're jumping. That's really an easier way to ingress a rover on the lunar surface. Per testing we did on the reduced gravity aircraft, right? Okay, so I think we've covered walking down here. This is key as well. If you ever want to decide if a suit was built for a partial gravity environment or a reduced a microgravity environment, look at the boots. If the boots are like the clown shoes of the EMU, the big stiff soled boots that give you stability when you're in a foot restraint, it's for a reason, right? It's not just because it's fun looking. That's because you are now in a microgravity environment. You want to get in a foot restraint, and this is all now very stable for you to do upper body work. Okay. If you have a boot that looks much more like a hiking boot, you're talking now planetary surface. Okay. You want the kinds of shoes you want to have for off-road trekking when you go backpacking, because you want that kind of grip, you want that kind of stability, and you want that kind of mobility out of it. You need flexion in the sole, those kinds of things. 16G, you can cheat some. Dutch boots designs have been out there because you really don't touch the ground very often. Really, that you don't get that flexion in the boot nearly as much as you would on the 1/3 gravity surface. But it's something that will usually give your planetary walking suit away. And then, of course, there's the environmental protection garment, right? So there's the part of keeping you protected from the thermal extremes, different dust, all those kinds of things. Okay. What does that look like in various forms? So part of my job has been to look at different architectures, joint designs, component designs, technologies, and try to incorporate them into suits, prototypes, so that we can better understand how these perform, what they're good for, what they're not so good for, when they're best applied. That has been a lot of my job, is having that toolbox of how best to build a spacesuit for different situations. Okay, so the Mark III, the waist entry eye suit was also early in my career. It was about 1997. I was the lead of that suit design. It's an all soft goods suit, other than some of the hatch components. Rear entry suit we bought off of from ILC Dover. After they were done using it, we got the seconds. It was good still. And then the Z1 suit we built, that was partly built to interact with the suit port, because we did build in the suit port interface plate into that suit. We also built in all of the waist mobilities. So you have waist flexion extension, right? And don't say this is flexion extension, this is hip flexion extension. This is waist flexion extension. So spine, think spine mobility, rotation, and add ab. Right? So pick up the briefcase, We don't usually put this in the suit, but can you? You can. But when you do that, you have all these different joints in here, and each joint you put into a spacesuit takes up space. Your body does it all kind of with your spine, so it's really spiffy. But when you have that stack up, then you need people. I was on an airplane going on a business trip, and there was this person in front of me, this man, and he was reasonably tall, but his torso was so long. And I was like, ooh, I almost touched the man and said, hey, where do you live? Because I wanted him to come be a suit subject for us, because we only had a few people who could fit with all those 3 waist mobility joints in the suit to do some testing with us. So it was funny, but we got to learn some of those things there with the Z1, as well as some hip design information. And then with the Z2 here, I don't know how to get rid of this screen over here. Z2 was the predecessor to the Exploration Extravehicular Mobility Unit, or XEMU, the next lunar suit design that NASA was building. So Z2 is a 2-bearing hip suit. Why is it black? Everybody asks. It's black because it was fun. We did a public engagement activity with the suit contract, where we had a university design team work with us to get some different inspirations for what the design of the suit would look like. The cover layer, just the cover layer. It's not an actual functional environmental protection garment, right? Environmental protection garments are white because of thermal considerations. They are white for functional purposes. Okay, if there's something on your suit that you did just for cool, you don't have good enough requirements. Okay, so It is black because we did a exercise with the university, and they had this kind of, it was kind of a bio theme that they were working on, and bioluminescence kind of idea going here with the black cover layer. So, okay. But let me go. I don't know if I can go back. Yes, I can. 1989, 1997, 2005. This was more like 2009, and this one was more like 2015, 16. So it looks like we have a lot of them. It wasn't an everyday thing, just so you know. It was a big deal when we got a new suit in. Okay. And the whole point of these is to allow astronauts to go out in the environment that they're going to work in and do their job. Okay. They don't want to think about staying alive. They don't want to think about how they need to move. They want to go do the work, be productive. Okay. So this is what we're asking them to do. Go be geologists, go collect rocks, go find neat stuff. And they want to be able to do those things. So collecting samples, kneeling on the ground and picking up a rock. Who knew that might be a thing? And then the fun part is geologists like hammers, and chipping rocks with a hammer in front of your helmet is a thought for spacesuit designers. Okay, and this is something that I think we all know. I do this public presentation to a lot of university teams, but how the design process works, right? But when we're talking about human-centric hardware, the key is, how do you know it's good? Some days as an engineer, I wish I could just be a mechanical engineer and go, hey, I have a range of motion of 360 degrees on this bearing, check, mobility is there, right? But that is not how we evaluate spacesuit performance, okay? How do we evaluate spacesuit performance? We said this before. You stick people in them and you see if they can do the jobs they need to do, okay? And so that, as you know, takes a lot of different testing with a lot of different people for everybody to go, yep, it's good. And we're ready to go, and you can fly it. So no matter how many numbers you have that you say your individual components do their jobs, it really comes down to that user acceptance. This is probably not a new idea to anybody here. Okay, so let me see where we're at. We're doing okay. Okay. We just said this, right? There's objective requirements, right? How many degrees of rotation does this bearing have? It's kind of a silly question, 360 degrees. But really it's the customer acceptance. So human-centered design is a thing. What does we do these objective tests. So what does that look like? Well, here's a spacesuit on a table with some instrumentation on it, and we are moving it through a range of motion to understand what the range of motion is and what the joint torque is of that range of motion. Okay. But when you're doing the task, what you really care about out of that knee is, does it let me do what I need to do? And you can see here the Apollo suit versus the Mark III, kneeling on the reduced gravity aircraft. I think that was 1/3 gravity. And it made me respect the Apollo astronauts a lot about what they did and how they did it in the suits that they had. The Apollo suits were a 3-in-1 suit. They did microgravity EVA, crew survival, and planetary surface EVA. Okay, crew survival and EVA suits are in the same branch, EC5 right now. A lot of people think the overlap between those two, if you're looking at a Venn diagram, is a lot. It is not a lot. Okay, they are both pressurized and they are both garments. Done. Really, because if you think about it, a crew survival suit is only pressurized, hopefully less than 0.1% of its use for needing it to be pressurized. Okay, sometimes they do it for comfort, but really, hopefully, only in a very bad day scenario that you never experienced does that suit really need to do what it's been designed to do. Okay, whereas the EVA suits always should be pressurized unless it's a very bad day scenario. Okay, and that one difference there is a whole different direction in how you work that design. Okay, another piece of it is landing. We did some tests during the Constellation program that were really unnecessary, but we did them anyway to prove to people who should know better that they should know better. But if you have a crew survival suit and you want to take a hard landing, okay, but you still want to combine better mobility. So let's put a waist bearing in it. What's going to happen to your spine? It's going to break. It does break. We broke them. I mean, this is something you never want to have to do, but we did cadaver testing. Okay. And so we got bodies, and we put them in suits and we slammed them, and we broke spines, we broke clavicles, we broke all kinds of stuff. It doesn't work. Okay. Crew survival suits built to do their job well is a very different animal from an EVA suit built to do their job well, especially a walking suit. Okay. You just got that. Well done. It took 3 years for some of my managers. Okay. Sorry. Am I talking like I'm a retiree yet?
I'll give you the application.
Thank you. So, but you see these things and you see the questions come up again and again, and you're like, dude, I did this. Just go back and read that report. But this is, again, that timeline that shows you the kinds of different prototypes that we have. This one is fun. This is a D suit. So we're super creative. The I suit is from ILC Dover. I suit. The D suit is from the David Clark Company. The D suit. Okay. But the D suit was supposed to be basically updated design of the Apollo suit reference, same kind of architecture and things. Guess what? It still moves like the Apollo suit. Just saying. So that kind of shows you our timeline there. This was 1 year of testing during the Constellation program. Okay, 2007, we were deep in the Constellation program. This is just the test links of each of those tests. This doesn't talk about the prep for the test. This doesn't talk about data analysis or report writing for the test. This was the testing that we did that year. Okay, it was a lot. And just some of the kinds of tests that we do. Now they do, real-time motion capture, but we used to do photogrammetry. I'll show you some pictures of what that looks like. And then you can see some of these other things where you actually do some work in planetary gravity, translation and mobility, right? We desert rats. You've got the treadmill kind of tests, the walk back, CO2 washout, those kinds of things. And then also the NBL is another place we can go. And this is just a short list, right? This isn't comprehensive at all. So this very unexciting photo shows our subject going to here to get this range of motion. But this is, I don't know why this is the picture that I had, but this is the least exciting of the ranges of motion pictures that I have. But that's what it looks like. And now you just put these little balls on it, infrared balls, and then they just move and they collect the data right there. The interesting thing about that, though, is when you're talking with biomechanics folks, they do every range of motion on a plane of the body, right? Which I don't understand because the human body doesn't work like that, but that's how they measure it. So like there's the plane that comes through here, there's a plane that cuts you in half this way. And so they want to measure on that clean plane, right? But when you're in a spacesuit, because of the angle that your shoulder's in, that motion is a compound motion immediately. You're not in one plane or the other plane. You are in multiple planes at the same time. So how do you understand that range of motion with the data that you're getting? That's been a difficulty when working with the SK kinds of folks for a long time, the human factors folks at the Prometric and Biomechanics facility. Okay, and then this is always a good slide if you're not familiar with the reduced gravity aircraft. Who got to fly on the reduced gravity aircraft? A good number of folks. Okay. It's called the Vomit Comet for a reason. Not my first, but one of my big weeks on the RGO, we were doing a week-long test series. And so one of our days, we did 2 flights in the day. Each were scheduled to be 60 parabola flights, but we did 62 parabolas. So I did over 120 parabolas in a day with what was the barbecue place out there? PD's, a PD's lunch in between. Woohoo! If you're going, go. All right. So we were ready for it. It was good times. I was driving home after one of those weeks when I was taking the medication to fight back the, the nausea. But it's an upper and a downer all at the same time. So it gets really funked out. And I was driving home going, oh, I shouldn't be driving a motor vehicle. I got home. It was okay. But this is what it looked like. So again, that's the waist entry eye suit moving. And you can see it doesn't have a waist bearing. So you can kind of see it doesn't look quite right. But still, you get along pretty good. You can get some good speed. And then over here, you can see we're doing the kneeling test. And you can see the Apollo suit, because it didn't have a lot of waist mobility either. It doesn't feel very stable, doesn't look very stable in that kneel. But what the Mark III could get down and up and down and up like 3 times before the Apollo suit really kind of got to where it was kind of balanced in that posture. Okay. Desert rats. So let's go out into the desert for 2 weeks and do spacesuit testing. You'd be surprised. People get really worried about dust. It wasn't that huge of a deal for our suits. Things do get somewhat dirty. Over 2 weeks, we'd have like wind devils come over us, dust devils, and go right through us. We throw a towel over the neck ring of the suit and go, ah. But when we come home and clean out the suit, it really wasn't so bad. It's the longer missions like a Mars mission where I think, or extended stay on the lunar surface, where you're going to need to pay more attention. And we didn't really have the right kinds of seals or designs for protecting against that in this suit. But we're looking at hatch sizes, and you can see right away, need some kind of handhold somewhere for them. And then this is that meteor crater on the bottom there. So we had them walk up to the lip of the crater and kind of get a really neat shot. Thanks to the NASA photographers, we always had one along with us. And then up here is actually near Baker, California. Yeah, Baker, California. And that's a robot from Ames called the Marsicod. And this is a good story too. We were on the phone talking, back in the day it was the phone, right? We were on the phone talking with Langley, and they said, oh, well, how fast does your suit walk? And we're like, it's not really, it's a slow walk, right? And we said, well, and how fast does your robot move? Oh, it's a pretty good robot. Here's their pretty good robot. So our subject was like, and waiting for the robot going. He got so mad at that robot. That's when you learn the lesson that you need to actually talk about rates of speed instead of just the qualitative measure that we were going off of. Geology testing, power, acquisition of power. This is a simulated solar array that we built the little cart. We made, we came in on a Saturday, we made the solar panel, and it was really neat. We had a good time. And then down here is a lunar rover. We initially borrowed the original lunar rover trainer from the museum, and they said, just don't mess it up. And we said, okay. And so we used that the first time we got to do the testing. And then I remember it was at the end of the test, we were just cleaning things up, and they said, well, we need to get back in the museum. And it's like a Sunday. And we're like, okay. So the group of us, don't tell, picked it up, and rolled it in on the side and put it down, and ta-da, it's back in the museum. So that's how that worked. And then after that, the robotics group built their own so that we could drill holes in it and do all kinds of fun things with it that we couldn't do with the lunar rover trainer. Okay. That was really cool, because we were at the spots where the Apollo astronauts trained using their lunar rover trainer, doing some things, prepping for the next time we go to the moon and onto Mars. This is a big horse treadmill. Okay. Yeah. When you have a suited subject, the regular old treadmills don't work. And this is a predecessor to Argos, which is the Pogo, and I don't even remember what Pogo stands for anymore. But it was another offload system. And so our subject is walking at a 1.6G gravity, and we're trying to understand what joints they use, how do they use them, what their met rate is, how long can they go, how fast can they go, just all those kinds of things that you don't know until you try. And this one is super, super cool. The PLIS team and the pressure garment team typically work fairly separately. Okay. They go off in their labs and tinkle with their little boxes and fans and pumps and stuff. And we, are in pressure garments walking around doing our thing. Well, this was the first time that the Bliss had, since really the Apollo Bliss, because the EMU Bliss isn't a lot different than the Apollo Bliss was. So new technologies, new design was put together in a full system, because Plisses are expensive. And so we've been able to build little piece parts and work on technologies, but never put a whole Pliss system together until then. And so this is the first time we put the new Pliss with a human in a suit. That's a Mark III, not a new suit, but still, and had them work together. Okay. And so we got feedback from the subject about how the Pliss was performing, which is very cool. And they were like, what? Oh, here's another story. I shouldn't tell this, but I will. Being recorded, it's okay. Pliss people think about humans as meat servos. Okay? They are just the thing that moves the suit and produces CO2 and humidity and trace element gases and that stuff, and uses oxygen. Okay. So they like to dial your subjects like they're just another knob on their Pliss performance meter. So they had one of my subjects, they said, hey, would you be willing to work at like, I think it was 3,000 BTUs, which is a lot of, it's hard work. It's like extreme exercise for, I forget, it was a lot. It was a long time. It was more than I would have asked. And because we have a subject, one particular subject especially, who likes pain. Yeah. He does. He's one of these guys that does these 100-mile races and things and smiles the whole time. I've got pictures. He does. So the more you push him, the more miserable he is, the bigger his smile gets. It's weird. But he was the one that they asked to do that. And so he said, yeah. And when I found out about that, I lost a gasket. That was not part of the tiara. That's not what we said we were going to do. And why did you think you could just tell my subject to go work it at 3,000 BTU? But anyway, that's the kind of, when you're not used to using humans as a part of your system, your test system, you're not aware of some of the things you need to think about. Again, it's not just a dial you turn to get the data you want. It's a human, right? So you got to think about that. It was a big day for us when we got to put the suit in the NBL for the first time. So this is the Z2 suit in the NBL. And because the suit was deeper, chest to back, we wanted to make sure that we could get through the space station airlock and hatch, and we could. They had to use a little bit of different techniques, and it was a little kind of more fine, delicate task, but they were able to do it. So that was good to know. Okay, again, you don't know until you try. This demonstrates some of the mobility that you could have in the lower torso. Some people were very concerned about using a mobile lower torso in a reduced gravity EVA. I'm like, well, it has its benefits, people. So this is a much easier way to get into a foot restraint than kind of the blind stab that they go at now. They get good at it because they practice it, but it's not the easiest thing in the world. And then there's an EMU with our Z2 suit in the NBL. Okay. And then let's talk about getting information from humans. Again, not just a machine that you get numbers out of, right, readily. So you have to create these kinds of rating scales that allow you to get the data that you want, okay? However, like this one, have you ever gone to the gym and just had a bad day at the gym? Everything felt hard, even if you knew you weren't doing your hardest workout, right? And other days you go to the gym and everything's just moving and you're on skids and you can do twice as much as you normally do and it just feels good. Humans rating their perceived exertion doesn't work very well, okay? Some days it's after I have a big meal on a cruise ship and I have to walk up all those stairs. That is an extreme exertion, okay? Going up when I'm headed up to, get ready to, for me, it's reading a book, then that's easy to run up those stairs, okay? So you have to be real careful with how you do this, and you need to work with your folks in human factors to make sure you're using the right scales the right way to get numbers out of humans. The reason you want to get numbers out of humans is because although, in my opinion, humbly, the actual comments that you get from your humans is the most valuable data. It is the data. It is the data. This is what your managers want to see. Is it good or is it not good? Okay. So if you put a number on it and the number says it's good, everybody's happy. Okay. So that is one way you can use these scales. Another thing, especially when you're using test subjects who aren't as familiar in the suit and trying to communicate where they're feeling something, that diagram over there with the different numbers on the human body helps you a lot for them to be able to identify where they're feeling something. When you're in a shell trying to move, it can be really hard to say what you're feeling and where you're feeling it. And so things like that are good tools to help the subject communicate with you. Okay. Or there's your modified Cooper Harper, your standard Air Force kind of flow chart about how bad is it kind of a thing. So you ask questions along the way that spit you out to different levels, and then that kind of defines how that system is performing when you give it that rating, which is another helpful way of doing things. As long as everybody's on the same page about what that all means, that's the appropriate scale to use for that test in that situation. Okay, you can't just pull these out of a book and go, look, I got a scale. You have to think about what you're doing. Okay. And that got us to where we got to actually NASA designed a exploration extravehicular mobility unit. Okay, so we were building the next moon suit at NASA Johnson Space Center. And we got it to the point where we had the suit assembled, the plus assembled, we could put them together, and we were ready to do testing to qualify the suit for flight. And that's when we got not to do that. So now I think you all are aware that we have the XEVAS contract. And so there's two different vendors working on doing different kinds of tasks, such as space station suit or a moon suit. And I've got, sorry guys, but I've got opinions about that. Of course, I think everybody does. And a lot of people are going to learn a lot of things. But I worry. I worry because I know how much there is in here. I mean, when you're sewing a spacesuit, and you do still actually physically sew a spacesuit, the not just the thread you use, but the tension on the thread that you use, the oil in the machine that you're using to sew the suit matter. It all matters. And so if you haven't seen the failures, if you haven't lived the loss of crew members, if you haven't done those things, if you haven't had the fear of losing a family member in you, then you aren't as potentially as aware of what you need to pay attention to, right? So those are things that do keep me up at night. Okay. And we've got, the thing I like to say about this slide is there's different spacesuits, and I think you can understand a little bit why now. Spacesuit design is predicated on where you're going and what you're doing. So if you're going somewhere different or you're doing something different, the spacesuit's going to look different. Like I said, if you're designing for looks, you're not doing it right. One of the things that Joe and I used to do on a Friday afternoon, he would take me to the lab and we'd sit around the Apollo suit, and I would be poking at different features on it, and I would try to figure out why it's there. Because Joe's, not the trick, but Joe knew that everything on that suit was there for a reason. Even if it was just a tooling mark, right? It was there for a reason. So you've got way too many requirements, way too much more important things to worry about. The suits are beautiful because they're keeping you alive and they're letting you do the work you need to do. You don't need to prettify them. They need to be beautiful because of how they perform, right? And that's why all these suits look different, because they're doing a different job, going a different place. Okay. We talked a little bit about this, and I'll try to get to the end of this so we can ask questions. Objective data can be very hard. We talked about the whole, getting real-time motion data out of suits. And like on this test down here at the bottom, we had subjects without the suit on, trying to look at what their unsuited performance was versus their suited performance. We were getting more range of motion in the suited performance than the unsuited performance. And you're like, yeah. So tricks there, it's an issue. And like this picture on top with the glove with all the wires, we know that working in the gloves can cause, there's a technical name for it, but for you to lose your fingernails. Okay. And so we're trying to understand more about that. And so we're trying to build gloves that have sensors that help you understand that. It took us 2 years to develop that glove. We used it once, it broke while we were using it, and we have a whole bunch of data that we don't really understand yet. Do we know that the length of your EVA matters? How often you do EVAs matter? How humid the suit is matter? Yes, we do. Okay. So when do you dive into the scientific root cause analysis enough to really go, look, here's my data that says it, versus here's my experience and these are the things that I can connect to it, and this is a problem, guys. We need to keep our suits less humid, right? That kind of thing. So but numbers, managers like numbers, so that's one of the reasons we chase those things sometimes. So I think I'm gonna go past this. You guys know I talked about being a test subject. It's hard to be a good engineer, suit engineer, without being in the suit. So one of the things I got to do was be a test subject, and it does a few things. One, it makes you appreciate the hardware you're working on. Okay. Another thing is it makes you a better test planner. You participate in one badly designed test, and you're like, I'm never going to make my subject do that ever again because that sucked. So here's where you kind of learn about how to really think about being the subject and being kind to your subject as you're doing testing. Okay. And then also as a test director, and I say, don't make your subject just stand around like that. And here's my subject just standing around in the spacesuit. But how do you put the test together? What do you think about in that? We had weather issues. We had hardware issues. We had one technician one time blew up our power converter because he connected it backwards. And so then we're like, so what are the things as a test director do you need to think about? It's like planning a space mission. When you go to the moon or Mars, what can go wrong that's really, really going to be a problem for you? And how do you have backup for backup for backup of that? Right. So, we're trying to understand how you pick how many crew members you need to send to Mars. Well, what number of backup crew members do you need to have? How many of those crew members are, well, if somebody goes down, can't work, what critical skills are there that need to be available in another crew member, that kind of thing, right? Okay. And sometimes it's way better to be the test director than the test subject. So, and this is where we'll go into questions.
Yeah. So what's going to be the difference designing a moon suit versus a Mars suit? Is it one suit for the entire inner solar system, or are there going to be different?
So this is.
Are we ever going to get away from white spaces?
Unless they figure a better way to do the thermal management, it's a white space. Yeah. So the question was, so is your Mars suit and your moon suit going to be different suits? And then are we ever going to get away from white suits? Here's what I have to say. If you're doing it right, you're testing what you need on Mars on the moon. So if you're doing it right, you're designing your Mars suit and using it on the moon. Yes, the environmental protection garment is going to have some changes because of the environments that you're in. The dust or the dirt is different on the lunar surface from Mars. On the lunar surface, it's more broken glass. It's a little electrostatic. It's not chemically reactive. When you go to the Mars, it's a more clay-like, a little stickier that way, and then it is chemically reactive, and it's not the broken glass kind of shape that the Mars dirt, the moon dirt is. So yeah, you need to think about what you're doing there, but the scale of a Mars mission drives your requirements. And so if you're not thinking ahead and pushing those requirements 3 years, potentially 30 to 500 days on the surface, having the backup systems, having the autonomy of the crew member cooked into the suit, right? If you're not doing that now, you're losing opportunities that you regret later.
So it's not really a thermal difference issue. It's between the two. It's really a surface environment, chemical, rock, and duration.
I mean, the thermal environments are a little different, but not, I mean, it's a little colder on Mars, but if you're going, well, so I used to say that it used to be colder on Mars, but then they said, hey, let's go into a PSR, permanently shadowed region on the moon. I was like, well, what the heck? I had always been Joe and I had trying to bracket the requirements that we needed to kind of think about for exploration, right? Because nobody was telling us, so we did that. And we never considered permanently shadowed regions on the cold side, right? That was just, you'll send a robot there. You'll never put people there. That's just silly. Guess what? I don't have any technologies developed for putting a human in a permanently shadowed region because that wasn't ever anything I thought was a realistic task doing in technology development.
One other quick question, those rear entry suits in an emergency situation, can the guy get himself out of that by popping that back door off? Or do they need assistance getting out?
I thought I had a picture. I don't. So the Russians have a rear entry suit, right? Russians can don and off that suit all by themselves. However, we've been trying to work on it. It is an engineering problem. It is not it's not a huge problem, but it is a tricky engineering problem. So there just some time and effort needs to be put into it. The trickiest bit is in a planetary suit, especially Mars planetary suit, you know how a backpack, you've got your shoulder straps and your waist belt, and you can manage the weight between those two things. Okay. Well, you kind of want to do that with a planetary suit, as well as being well integrated either by doing my dad's method, which is do the sausage skin in a sausage in a sausage skin kind of method of fitting into a suit, or you make sure you're integrated with the suit by having the shoulder strap and waist belt. Getting that self-don, self-doff is a little more challenging. I don't think it's insurmountable, but it's a little more challenging. Yeah. Because if the suit fits you right, it's fairly close fitting, right? So there's not a lot of room behind you first, and yeah.
Yes.
I think you know
I have got a screen that I need to put in a very west facing.
Did you ever
Installed.
officially or unofficially
Actually put up some other makeshift things that I want to get rid of, so I'd like to get something.
expertise on questions?
And it's 24 and 4 inches long.
So
Not opposed to having two systems,
For a lot.
because one section would be for.
the question was that my dad is Barry Ross. He flew 7 times, so a lot, and did a bunch of EVAs. Not enough.
Sure there
Yep.
is.
Those of you online, could you please, Keith, mute your mic? Thank you.
Hold a second.
Okay, so did I ever take advantage of knowing my dad? Yes, I did. So it was funny because when I was a baby co-op, right, and I'm sitting on the back row because I'm just watching. They're talking about some issue that was critical, and Dad was the EVA chief in the astronaut office at the time. And somebody said, "Hey, Amy, can you ask your dad?" And I was like, "No, got it." And so, because we were driving back and forth to work together, so I just, "Hey, Dad, I got this question. What do you have to say?" And so I would take it back to the team, and they're like, "How does that check? No, what?" Yeah. So, of course, and that didn't start when I started working. Dad was a dedicated astronaut. He cared about how well he performed things. He was always looking to improve. So he would do things on Saturday afternoon, like pop in a videotape of his what if run and watch how it went and what he could do better. And so I'd sit there and he'd talk about what's going on. And, I wasn't like scholarly observing this, but I did hear, I did watch, I did see. So I was absorbing things as a kid, and then it was very well applied, I hope. I think. And the other thing that was neat was Dad was one of the few crew members who worked with Joe on advanced suit development. Sonny Carter and a few others did that too. But a lot of crew members weren't familiar with advanced suit development. And so that was nice to be able to talk to Dad about some of those things that we were working on too, and get some input and share some experience and some test knowledge that he had. So
one of my proudest days was when I transitioned from being Jerry Ross astronaut to Jerry Ross, Amy's dad.
Yeah, thanks. You had a question first.
Oh, yeah. So, a couple of questions. One of them, have any of these suit experiences or lesson learned captured in some sort of book or repository? I mean, what I see is that there's a lot of new engineers
Yeah.
on the spaces that have very limited experience with like why we are in the place that we are in.
Yeah.
I particularly don't see how we can get hands-on approach.
Well, so that's unfortunate because their efforts are being made, right?
Okay.
So talk to some of your managers if that's you're not seeing that information get to you, because we were asked to prepare, gather, provide that stuff. Some of it is within Collins. I know probably walled off Collins, but the experience with EMU is a big piece of it.
Yeah.
But we have, failure logs and things of some of the work that we've done, like XEMU runs and that kind of thing. So that information about what didn't work, how we fixed it, all those kinds of things are out there. So, yep. Yeah, Mark.
Yeah, so I was wondering if you could talk about, since you've been in all three, are there any notable differences between the 1/6 gravity and the Argos and the pool? I mean, you can tell you're hanging on the Argos maybe, and you can't with the actual 1/6.
Yeah.
But other than that, anything notable?
Yeah. So this is where I really, really feel the lack of the reduced gravity aircraft.
Any questions?
Oh, so the question was, can you tell the difference in like a reduced gravity aircraft versus Argos versus NBL experience, right? And you guys know every test facility platform offers different benefits and it has different deficits. So you just need to know what you're working with and know what you need to pay attention to and know what kind of things you need to take account to in your understanding your data and how you analyze it. But the key piece we don't have today is the ground truthing, right? So we can work in Argos, and yes, it feels like you're being picked up by the soles of your feet. And the other weird thing about Argos is that, like, if you want to kneel, you think about gravity pulling you down. Well, in the Argos, you have to actively work to get down, and that's not how gravity works, right? So that's a weirdness in Argos. Another bit that's people talk about that could be a factor is your arms aren't offloaded, right? So if you're doing a lot of arm intensive stuff, your arms could get fairly tired because they're still 1G, even though the rest of you is supposed to be 1/3 or 1/6G. And then it's a smaller volume. They're building something called Axis now, which is, I don't know, 2-3 times the size of Argos. But it's still, people take a lot of space if they really want to get running, which is one of the reasons we did Desert Rats, right? There's just a bunch of space out there. So again, it'll still give you a certain, like in Argos, you can only get like 2 or 3 good steps before you need to start stopping. And our Axis will give you more of that, right? You'll get you'll get up to speed and be able to walk at that constant speed before you have to start stopping. So that'll be nice. NBL, water viscosity, huge, right? I mean, come on. You've all tried to walk in a pool. Does it feel normal? No, it is hard. So the way out matters a lot. We still haven't got the way out right. And it's an issue. So if you don't understand what's NBL artifact versus gravity artifact, you're in trouble. How do you understand your data? And the one thing that we had was the reduced gravity aircraft to go, oh, that's what we're shooting for. This is how Argos is different. This is how the NBL is different. So that's how we look at this data. We don't have it. So there's a whole bunch of engineers out there trying to do this stuff with no real understanding what the environment they're working in is, right? Which is not good. And that is not how we built Space Station. Yeah. Yeah.
On Mars, you're gonna have twice the gravity that you had on the moon. So is that gonna be a big factor? I mean, that's now load on the person in the suit.
Yeah.
To actually have to fight for gravity.
Yeah. So the question was the one going from 1/6G to 1/3 G, how much of a factor is that? It's pretty significant. Mainly because you can cheat a lot in 1/6 gravity. 1/6 gravity is just enough gravity to kind of be annoying. You like to feel like you're a micro G, but you keep falling to the ground slowly. So one of the reasons you saw some of the gates that they had during the Apollo program was the suit mobility, but some of it's just that's the easiest way to move in 1/6G, because your touch time and your touch force when you actually touch the ground is so short and small that you really have to kind of plan that next step, because you're going to be hanging in there till you hit the foot hits ground again, right? And so you have to kind of think ahead about how you're moving. 1/3 G feels much more 1G like. Okay, and that doubled mass that you have, so you walk, the movements is a lot more 1G-esque. So you can do a lot of testing in 1G and think, well, that's pretty normal, right? It's just the mass of your hardware starts to matter a whole lot more. Not to mention you're going to Mars with it, but just on the surface, it matters more. Yeah.
But bodily, he's gonna be worked out a whole lot harder. In that environment.
If we, so mass reduction is always at the end of a program. They always run out of time and money. You can do it. It just takes time and money. And so can you get mass down? Yes. Are there technologies we should be investing in to get really mass where we need it to be? Yes. Are we? No. Right. I mean, these are not insurmountable problems. It's just time and money. Yeah. Yeah.
So are you, Boeing, SpaceX, Axiom, they're all developing their own version of spacesuit. Are you working, or is your group interfacing with?
Oh, well, now we're talking apples and oranges. Okay, so Boeing is building a crew survival suit. Are we working with them? Yes, we are, as they ask us. So the way this is set up now is that the vendors are responsible for their hardware. They build it, they test it, they report some information to us that we required in the contract. But other than that, it's their hardware. So we have a certain amount of insight, but not like we're used to on a standard NASA contract, right? So it's interesting to try to see how this is going to play out and work. It's uncomfortable for NASA, right? But if NASA starts to be more involved, then you guys don't know, but this is how it works in the right. We all know in the room that then fingers go, well, NASA said, or NASA told me, or NASA, right? So then it's NASA's fault, and then it's NASA's cost and NASA's schedule slip, and we're trying to not the whole point, but a big piece of the point is to make the contractor the responsible party, so that they have to go be really dedicated to solving their problems in a timely and cost-effective manner, right? And that's part of the driver of doing it this way. Not just that, but to also develop a greater space capability in the United States, right? So, yeah, Dad, and then Joey.
Yeah, looking at all your pictures of people in spacesuits, it looks like a lot of fun. But it's not. Being in a suit for extended periods of time is quite painful. I still have places in my body that I have marks from those hours that I spent in suits.
Yep.
The question is this: for a 6-hour run, once a space flight or something like that, you can tolerate that and come home and let the bruises and things repair themselves, and it's okay.
Yep.
When they go to the moon, and certainly when they go to Mars,
yep,
their purpose to be there is to go outside repeatedly every week.
Every other day.
Well, okay. Yeah. So my question is, how do you provide them with the comforts that they're going to need so that they don't have bruises and lost fingernails, yep, and everything else that puts, yep, them out of the practice or out of the mission?
Yeah. So the question was, how do you design suits for exploration missions, extended duration lunar or Mars missions, where the crew member can use their suit repetitively, like wearing a pair of overalls, and not get hurt like they do currently in the EMU and other suit tests? So it's a good question. What I've always wanted to do, but you saw it looked like a lot of suit prototypes, but it was one of, a few of them every decade. So we didn't tend to take our suits to the kinds of use rates and hours that we expect to need to be able to do, and break the suits and do it over again and over again. So that's what I think you need to do. I think you need to put people in suits over and over again and start to really dig into how do you change it so it doesn't cause some of these issues on crew members. We're not unaware, we're not unsympathetic, right? As suit engineers, it's a matter of time and money, partly, but partly is fit. Okay. And so one of the things you can do if you're looking at missions, especially on Mars mission, you want to keep logistics where there's a lot of capability of switching things, right? You want to be able to borrow from Peter to pay Paul when you need to. So you want to have some kind of commonality in the different suit components. But if you can build more custom components, that's one of the reasons the Apollo astronauts were able to do what they were able to do. Those suits were customized, okay, and not to the full extent, right? Their wrist disconnects were the same size, their neck rings were all the same size. So there was some standardization, but they had some level of customization that also allowed them to address some of those issues better. Because if, like the D suit was one of the ways I learned that, but it's true with the Apollo suits too. It was designed for an individual basically at David Clark Company. When he got in that suit, he could do anything he wanted to in that suit. We get in that suit and we're like, It was terrible. So the sizing was critical to the functionality of that suit. So that's, I think, one way we can improve it. Again, with prototypes, we either build it really big so we can fit as many people in it as we can, or we build it really little because we're trying to understand how you package all the stuff you need to with all the interfaces to all the other systems in a plus and the rest of the pressure garment. So we haven't been able to explore some of those extremes, but I think Mars might drive you to get to look at that trade a little bit more.
But the higher pressure goes, the more that becomes a problem.
Yep. Yep. Okay, I think you had a question a while ago.
Yeah, this actually ties in well to what you just said about the pressure. So you said that Apollo was 3.75 psi, EMU was 4.3, and then we're looking towards 8 psi. That 8 number, can you talk more about why we're increasing it?
Yeah, so there's a few things. You want to be able to go outside and do work efficiently, which means you reduce the overhead it takes to get outside and come back in and turn the suit around to do another EVA. Okay. You also want to protect your human from things like decompression sickness, right? DCS. So the reduction in the change in pressure reduces DCS risk. So if you're going out of an exploration atmosphere 10.2 cabin to an 8 psi suit, you can get out and go without pre-breathing for 4 hours, right? In fact, you may just only need to pre-breathe like 30 minutes while you're suiting up and checking things out, and then go out and work. And then you can come back in and not have to worry about some of those physiological issues so much. One idea is, and this is what the exploration suit did, was that it had variable pressure settings programmed, right? It was a software setting, not a hardware setting, where you could say whatever pressure you wanted to have the regulator work at. So you could go out at 8 psi, and then as you're outside doing some work, you could bring that pressure down because you did a walking pre-breathe, and then you can come down to a lower suit pressure to ease some of the human considerations, and just not wear your suit out. Higher pressures are harder on spacesuits too. So, yep. That answer your question?
Yeah, it answers it. Would you still have the same level of mobility with the higher pressure?
Yeah, you do.
Okay.
If you design it for that higher level of mobility, Dad's not wrong. Dad's right in that it's recorded. It's recorded. It's recorded.
I want to record
it. So if your gloves are at a higher pressure, it's going to be harder to move your gloves, and that's going to cause more impact on the crew member. Okay, so you don't want to work at those higher pressures for probably a full EVA. It will have some impact, but it's not on the mobility. It's on the wear and tear on the human in the suit. No, you just design to that pressure and you get it. Joey had his hand up.
All right, before we take any more questions in the room, I want to make sure that we're taking care of our people who have joined us online. Do we have anybody online who has a question Keith's iPad, you've had your hand raised since remember when. Do you have a question for us?
Yeah, I did, and it had to deal with the the cycle suit. We also see with the SpaceX suit. I don't know much about the Boeing suit, but also with the pumpkin suit. You know, is there anything about the pros and cons for each? Because it looks like the pumpkin suit has a lot more mass than I saw with the cycle suit, and definitely less mass with respect to the SpaceX suit for launch and entry. I don't know anything about the Boeing suit, but can you expand on that a little bit?
Yeah, so Keith's question is with regards to crew survival suits. I am an EVA engineer. However, I have worked in crew survival to a degree, and the Constellation suit was supposed to try to do both, and we talked about that not being such a good idea. So it all, what you're trying to do with the suit matters. There are the whole point of a crew survival suit is to provide a backup to the crew member in case you lose pressurization in the cabin. That is the key requirement. You can make it do other things and help you in other ways. So our advanced crew escape suit, the ACES that we used at the end of the shuttle program, our Orion crew survival suit, they have some different functions and requirements than, say, the SpaceX suit. The SpaceX suit is a human-shaped balloon, okay? And did you notice it's kind of stylish? Guess what? That means it doesn't have a lot of requirements, okay? So it really is a pretty basic, keep you alive in case of a cabin depressurization, and they handle some of the other issues that you might work with a suit other ways, right? And that's a decision you can make. So you just have to manage all the risks and make sure that you've covered your ground. But they chose to do it one way and we choose to do it a different way. Okay. I don't know. I think Boeing is using a David Clark suit or an ILC suit. I'm not sure where they're at right now. But it's the same idea. It'll look a little different and it's going to, have a certain set of requirements and it will look accordingly based on what requirements it's being asked to handle. Does that help answer your question?
Well, I was just looking at just saying because each of the suits look to have like a significant different mass, and landed mass is actually a key driver on the spacecraft design. And so adding mass in does have an impact on what happens. So that's why I was asking about the drivers.
Right.
And the comparison between what's out there.
Your SpaceX vehicle has to take on more of the functions than the Orion's, because Orion's suit does the functions and SpaceX vehicle has to do the functions, right? I mean, that's how it plays out. There is mass somewhere to do the functions. It's either on the vehicle or it's on the suit. The mass is going to be there.
Okay, this is a good time. We were just talking about pumpkin suits and we have 0 minutes before. See, I told you. We have 0 minutes before we turn into a pumpkin and get thrown out of here. We'll take one more question and then maybe, just maybe, Amy
Joey,
will stick around for a
Joey.
little bit.
Yeah.
Okay, Joey.
Joey was up first.
Yeah, from your spacesuit design experience and excluding lunar dust and Martian soil, what's the limiting life item on the suit? Is it the wear and tear on the gloves?
It's still gloves.
Something about TMG and maybe having to replace it occasionally?
So we honestly don't have enough data to actually tell you that for sure, but I would say it's gloves. Oh yeah, the question, sorry, Joey asked was, what's the limiting factor, not accounting for dust issues in spacesuit design, spacesuit durability, basically. And that's where I want to go do that test where you just beat the suit. They did a little bit of it with the XEMU. So they started doing that work and they broke the suit several times and fixed it and saw what broke next, right? Which is what you want to do. But it's gloves. Gloves will wear out. Your TMGs probably first, EPGs, whatever, and then your actual glove structure. Yeah.
The rest of your confidence gonna have a fairly good life to it.
Pardon?
The rest of this good life.
Yeah, I mean, then you start to think about what your bearings are doing, right? And watch the dust seals and
Yeah.
that's where you need to think about knee pads and elbow pads, depending on how much you're down in the dirt. But I expect at least knee pads you'll want to have. Your boot soles, your ankle joint, you're going to want to watch, right? Just because they're exposed a lot and you're recycling them a lot. So that kind of thing. Yeah, I mean, it's not a real brain twister. It's pretty pretty logical stuff. We just haven't really got to beat it out to where we can say that with data. This is what happens. This is your problem, right? Yeah. Yeah. Okay.
All right, it is just a tad bit after 4 o'clock, so we're kind of going to have to close it off here. I do want to thank everybody online. We had a really, really good turnout today. Lots of people here in the room. Thank you for being here. I just want to remind you that I'm going to stop the recording here in just a second. The recording will be available on the NAL website within a couple of days. So, you know, Jerry, if you want to hear that quote one more time, you'll be able to go and absolutely. So all right, so just a couple of things to let you know about. The next First Thursday meeting is going to be on June 6th. Yes, the longest day. Hopefully it won't be, but we will be back in the Lone Star room here at the Gilruth. Theoretically, they've upgraded the infrastructure here. We'll also be on Zoom. Meanwhile, we do have a keg of the month scheduled. I put in a special request with the guy upstairs that the skies are going to clear right at 4 p.m. You heard the big crash right at 4 o'clock, so the skies are supposed to be clear. So join your friends and colleagues at the Bluebonnet Pavilion right outside for the keg of the month, and may the 4th be with you.